We will give you a brief overview of some of the attempts to reduce the sizes of large language models, LLMs, without sacrificing their accuracy or capabilities. Reducing the size of LLMs can have several advantages, such as 1. Accessibility. Smaller models are easier to train, run, and deploy for researchers and developers who do not have access to large-scale computing resources or proprietary APIs. Smaller models can also enable more reproducibility and transparency in AI research and applications. 2. Efficiency. Smaller models are faster and more energy efficient than larger models, which can reduce the computational cost and environmental impact of training and inference. Smaller models can also fit better on edge devices, such as smartphones or IoT sensors, which can enable more real-time and personalized applications. 3. Robustness. Smaller models can be more robust and reliable than larger models, especially when trained on more data or distilled from LLMs. One approach is to use sparsity, which means removing the weights that are close to zero in the model, since they have little or no impact on the output. This way, the model can be reduced in size and complexity, and run faster and more efficiently. However, sparsity also introduces some challenges, such as how to prune the weights without losing accuracy, and how to handle the irregular memory access patterns that sparsity creates. One example of a method that uses sparsity in LLMs is SparseGPT, which can prune LLMs to at least 50% sparsity in one shot, without any retraining, at minimal loss of accuracy. SparseGPT works by applying a global threshold to the weights of the model, and then fine-tuning the remaining weights with a sparse optimizer. SparseGPT can also work with different sparsity patterns, such as unstructured or semi-structured, and can be combined with weight quantization for further compression. Another example of a method that uses sparsity in LLMs is dataflow, which is an execution model and architecture that enables efficient on-chip irregular memory accesses as well as native kernel fusion and pipelined parallelism. Dataflow can help recover device utilization and speed up training and inference of sparse LLMs. Dataflow can train a 13 billion parameter GPT model with 80% sparsity to the same quality as the dense model, while achieving an end-to-end speedup of 4.5x over dense A100 baseline. Another approach is to use distillation, which means training smaller models on the labels generated by LLMs, instead of using human labels or the original data. This way, the smaller models can learn from the knowledge and capabilities of the LLMs without requiring large amounts of data or human annotation. However, distillation also introduces some challenges, such as how to deal with the inconsistency and noise of the LLM-generated labels, and how to leverage additional information from the LLMs. One example of a method that uses distillation in LLMs is knowledge distillation of large language models, KDLLM, which is a general framework for distilling smaller models from generative LLMs. KDLLM uses reverse Kullback-Leibler divergence, KLD, instead of forward KLD, which is more suitable for generative models, to prevent the student model from overestimating the low probability regions of the teacher distribution. KDLLM also derives an effective optimization approach to learn this objective. Another example of a method that uses distillation in LLMs is distilling step by step, which is a method that trains smaller models with LLM rationales as additional supervision within a multitask framework. Distilling step-by-step extracts the LLM rationales by using attention-based explanations or gradient-based saliency maps, and uses them as auxiliary tasks to guide the student model. Distilling step-by-step outperforms LLMs on several NLP benchmarks with less training data and smaller model sizes. A third approach is to use more data, which means training smaller models on larger and more diverse datasets, instead of using the same or less data as the LLMs. This way, the smaller models can achieve better generalization and performance than LLMs that are trained on less data or more biased data. However, using more data also introduces some challenges, such as how to collect and curate high-quality data, and how to deal with the increased computational cost and environmental impact of training on large datasets. One example of a method that uses more data for LLMs is Chinchilla, which is a 70 billion parameter model that outperforms the 175 billion parameter GPT-3 by training on nearly 5 times as much data. Chinchilla uses a dataset called Pile, which is a large and diverse collection of 825 gigabytes of text from various sources, such as books, Wikipedia, GitHub, Reddit, etc. Chinchilla shows that data quality and diversity are more important than model size for LLM performance. Another example of a method that uses more data for LLMs is LLaMa, which is a family of models that range from 7 to 65 billion parameters and outperform GPT-3 on most benchmarks. LLaMa uses a dataset called Meta, which is a massive and heterogeneous collection of 3.8 terabytes of text from various domains, such as news, social media, scientific papers, etc. LLaMa shows that using more data can help train smaller models that can still go toe-to-toe with the biggest LLMs. By implementing these approaches, researchers have made significant strides in reducing the sizes of large language models while preserving their accuracy and capabilities.